Thanks for joining and welcome to today's webinar on property values and water quality, supporting decisions with the Hedonic model. This webinar today is part of EPA's Office of Research and Development's Water Research webinar, bi-monthly webinar series. And so we have a great presentation today, but before we get started, I just want to go over a few items, things for you all to be aware of. First, a PDF copy of the webinar slides is located in the handouts in the right-hand navigation panel. In that same navigation panel, you'll see a questions box. So we'll be saving 10 to 15 minutes at the end of the presentation for a Q&A session. So we encourage you all to submit questions throughout the presentation in that questions box, and we'll get to as many as we can at the end. We have a very large audience today, so we won't be able to get to them all, but we'll do what we can. If you experience any audio or other technological issues during the webinar, you can let us know, and we can try to help you out. There's the email address on the slide on your screen, webcastinfo@cadmusgroup.com, or you can chat in the questions box as well. This webinar will be recorded, and so we'll post that to the Water Research Webinar Series webpage within a week or two of this webinar. That link will be in the chat box. And finally, moving on to the next slide, we will be offering certificates for this webinar. We just have a few requirements. So in order to receive a certificate, you must be registered for this webinar, or you must be in a room with someone who's registered for the webinar. You must attend the webinar for the full 60 minutes. And finally, this only is relevant to people who are watching it with other folks in the room. So if you do have people who are watching in the room with you, we ask that you submit those names in a web form. The link is in the questions box. You can also access it through the PDF handout. And that way we can give those folks certificates of attendance. But if you're watching it alone and you requested certificates at registration, you'll receive one, so no need to fill that form out. Great, so moving on to the next slide to go over a few announcements. We have two upcoming EPA webinars. Tomorrow we have an EPA training webinar, and that's going over the Freshwater Explorer. That's tomorrow, November 19th. And on December 8th, there's an informational webinar about the request for applications for the deployment of innovative water technologies for very small drinking water systems. And I'll talk about that RFA in the next slide as well. So another announcement is just to let you all know of some research grant opportunities. So the deployment of innovative water technologies for very small drinking water systems, that's recently opened, and that closes January 12th. And you can also catch that webinar mentioned on the previous slide. There's also viral pathogens and surrogate approaches for assessing treatment performance in water reuse. That closes January 6th. And finally, evaluation of pollutants in biosolids, and that closes January 5th. And moving on to the next slide, I'm very pleased to introduce the presenters for today's webinar. So we're fortunate to have Michael Papenfus and Matt Heberling presenting today. And Michael is an environmental economist with EPA's Office of Research and Development, Center for Public Health and Environmental Assessment. His current research focuses on estimating the economic benefits associated with protecting water quality, wild salmon populations, and human health. Michael has a PhD in environmental economics from University of Wisconsin-Madison. And Matt is a research economist with EPA's Office of Research Development. Also, he's in the Center for Environmental Measurement and Modeling. His current research focuses on estimating the economic benefits of improving water quality and using economic incentives for controlling pollution. And Matt holds a PhD in agriculture and economics from Penn State University. And with that, I will pass the presentation over to Michael, who will kick off the presentation.
All right, thank you. Can you hear me?
Yep, and we can't see you yet, so if you could turn your webcam on, that would be great.
Yep, sorry.
There we go.
Okay, there. All right. Well, I'd first like to thank all of you in attendance. It's exciting to know that there's so much interest in our research, and specifically in our property value hedonic modeling research, examining water quality. Just a real brief overview of what we're going to talk about today. First, I'm going to go over a brief overview of what are hedonic property value models and how are they used. And then my colleague, Matt Heberling, is going to go through an in-depth analysis of a meta-analysis that we are working on currently, examining hedonic water quality studies. And then I'm going to come back on at the end and talk about future directions and research based on things we learned in conducting the meta-analysis that Matt is going to speak about.
Hey, Michael, real quick, it looks like your webcam went off. Would you mind going to that webcam tab and then click share my webcam? And then if you need to hide the webcams, great, it looks like it's on now. If you need to hide the webcam so you can see your slides, you could, in that same webcam tab, you can click webcams and then hide all webcams.
Okay, there we go. I can see it now.
Wonderful, thanks.
Okay, so what are property value models? We'll take a minute and imagine for a second that you're getting ready to purchase a home on or near a body of water. And of course, one of the first, anytime you're buying a home or anybody buying a home, the primary thing they're going to think about, they're going to think about, well, what's the size of the house? What's the square footage? How many bedrooms does it have? How many bathrooms does it have? But in addition to those structural and physical characteristics of homes, you're also going to think about, the location that you're buying the home in. And potentially you're thinking about attributes and characteristics associated with those locations. And if you're buying, imagine you're buying a home on a lake or a river or an estuary, water quality might be one of the things that you factor in to your decision on where to choose, which home to buy and where to buy a home. And so there's a rich literature out there that uses, that really focuses on this decision that home buyers make. And we can use those decisions, we kind of use those decisions to look and try to use them to examine how natural amenities, in our case, such as water clarity or other water quality variables, might be reflected in home values. And that's sort of the basic intuition behind property value models, is that when you buy a home, yes, you're buying the structure, but you're also buying a location, or you're making your decision based on the location of that house. So private markets for property reveal consumers' willingness to pay for measures of environmental quality. And that's why, environmental economists refer to these types of models as a revealed preference model, as opposed to a stated preference model where we don't actually observe market-based behavior. And that's a real advantage to the hedonic property value models, being able to actually observe real choices in the world that people make. And as I mentioned, when consumers purchase property, they're choosing based on the housing routes and, most importantly for our work, location-specific amenities such as water clarity and water quality, other water quality variables. And the spatial variation in these natural amenities, these are then capitalized into the housing prices, which we can empirically measure. And property value models have been used to value a wide array of goods, such as education, crime rates, proximity to open space, flood risk. And many other location-specific amenities. It's really one of the workhorse models in economics for trying to tease apart the value of different characteristics of locations. So one of the real motivating factors behind our research at the EPA looking at water quality is to be able to measure the economic benefits associated with our programs and our policies. And there's a large number of people working on water quality, air quality, and a host of other things. And one of the distinctions I like to go over is that, you know, when we're looking at the economic benefits associated with air quality and water quality, you know, largely when we're looking at air quality, much of those benefits are measured in terms of human health benefits. And we generally have a fairly good sort of pipeline for monitoring air quality, knowing where how air quality spreads over the landscape, who's exposed to variations in air quality, and then there's a rich literature measuring, you know, the effect of air quality on human health. And we'd like to develop a similar sort of pipeline for measuring the benefits of water quality. And one of the reasons why doing this in terms of water quality is I believe that it is more complex than in some ways than air quality, is that there's a wide array of end uses or beneficial uses associated with water quality. Water quality can simultaneously be sort of an endpoint in itself that people consume directly in terms of drinking water and other things, but it can also be an input to lots of other goods and services that we value. You know, it underlies recreation opportunities. It's used as an input in agriculture. It provides ecological benefits. There's aesthetic characteristics associated with water quality industrial. So there's a wide array of end uses associated with water quality that imply that in order to estimate, you know, the economic benefits of protecting water quality, and you really need to do sort of a wide range. You need to look across the range of those end uses. And the hedonic model is really focused more narrowly sort of on the aesthetic benefits of water quality. You know, hedonic models are not designed to look at the drinking water benefits or agricultural or industrial uses. So I want to go through a short example of some research that I've conducted in the Puget Sound using the hedonic property value models to give you an idea of how these models work. So I conducted a study in one county surrounding on the edge of the Puget Sound, and I looked at property sales over a range of about 10 years. And I basically used the property sales data to design two groups of homes. One group of homes that was located directly adjacent to water bodies throughout that county that had a water body impairment. Using data from the Washington State Water Quality Impairment Program that falls under the EPA's 303D program, which is part of the Clean Water Act, I compared homes that were located directly adjacent to these water bodies that have water quality impairments to another set of homes located within 100 meters or 500 meters. I had several contrasts, but which were located on water bodies that were unimpaired. And sort of the broad take home from that research was that, you know, homes located adjacent to water bodies with these water quality impairments sold at a discount compared to the homes on water bodies without impairments. And within this research, I looked at the effect of just having an impairment or not having an impairment, but I also examined the effect of different water quality, individual water quality parameters such as dissolved oxygen, temperature, E. coli, and I did a whole set of contrasts. But this is just one study that was conducted in one county in the Puget Sound, and really sort of opened the door in my head. Well, how would these results translate, or how might they vary if you were to conduct such a study in different parts of the country? So there's more work to be done, but I wanted to go over that just to give you a flavor of what sort of an individual property value study would look like. And with that, I'm going to now turn over the screen, the part of the presentation where we talk about a meta-analysis that we conducted looking at the literature on property value models and water quality.
Thanks, Mike. Can everybody hear me?
Yep.
Thanks to the attendees as well. This is great. So Mike just presented the hedonic approach and discussed how it can be used for a particular local or individual market. The example he used was for the Puget Sound. To support decisions for larger scales like regional or national decisions, we have to broaden the scope of our analysis. So I'm going to present some research that Mike and I have with Denny Ganay, who's at Appalachian State University, Olivia Griot, who's at Apt Associates, and Ben Holland, who was at Apt Associates. And that's for water quality decisions where there's no individual studies or where water quality decisions affect larger areas. And the reference and link to the paper are at the end of our presentation if you want to take a look. So hedonic water quality studies have a long-standing literature going back to 1968. Despite this, hedonic analyses have yet to be used in national or regional water quality decisions, and we're interested in attempting to do so. To our knowledge, no published study has examined the collective findings of this literature. Next slide, please. So our objectives then are to summarize the hedonic water quality literature and synthesize the results using meta-analysis. A meta-analysis is a systematic review or a statistical analysis of a specific topic. It is popular in the medical field to summarize results from medical trials. We want to estimate unit values or summary measures for different water quality measures and value functions in order to transfer the benefits to regional and national water quality regulatory decisions, those broader areas. That is, we want to estimate representative hedonic estimates and apply them to decisions that affect those broader areas. And we call this benefit transfer. Next slide. So generally, a meta-analysis has the following steps, starting with a literature review. Next, we define a summary measure of the effect, which for hedonic models are how house prices change, and we call these elasticities, and I'll define those in a little bit. Then in order to estimate a statistical model for the meta-analysis, we need to code the study characteristics. Then we calculate the summary measures or unit values. We run the models and test them and pick the best one for whatever policy of interest we have. And then we identify the gaps and limitations. Next slide. So step one is the literature review. And for our literature review, we identified 65 studies that examined residential property values and water quality. We excluded 29 of those studies for the reasons listed on the slide, including the study examining groundwater quality, not surface water quality, where it was outside of the US. Next slide. So out of the 36 remaining studies, the majority examine lakes and reservoirs. The asterisk on the lakes and rivers boxes represents that one study we found examines both rivers and lakes in the same study. So it is included in both categories. Next slide. Okay, so if we're going to analyze regional or national water quality decisions, we need to understand where the current studies were located. We identified 4 regions for our study, and you can see that most of the studies that we found in our literature review are in the Northeast, around the Great Lakes, and in Florida. A few studies are out west, but there aren't many out there. Next slide. So step 2 is define the summary measure, and we chose to model price elasticity. This is pretty typical for economic meta-analyses, although in some environmental economic meta-analyses, they use the actual dollar value estimate. A price elasticity in this study is the percentage change in the house price resulting from a 1% change in water quality. The principal advantage of elasticities is that they are unitless and thus allow for a comparison of results across studies. However, this was a challenge for our study to derive and estimate comparable elasticities across studies that accounted for the different functional forms, distances, and interaction terms in those original models. Our paper actually has a 47-page appendix showing all the derivations from all the studies that we found. We're also able to account for statistical precision around the elasticity by estimating standard errors using Monte Carlo simulations. When our elasticity calculations include multiple coefficients, so for example, when water area or distance is interacted with water quality in the original analysis, we require covariances. And we had to contact a number of the study authors to obtain these covariance matrices. One unique aspect of our metadata set is that we calculated separate elasticity estimates from the same original regression. For example, when feasible, we incorporated homes at different distances and created a waterfront and non-waterfront, which is within 500-meter estimates, which gives us a spatial aspect and allows for more detailed benefit transfer. Next slide. So here we list the 36 studies and the number of meta-observations by study. Each study includes multiple regressions estimated, or multiple study areas, or multiple measures of water quality that can provide a single observation. So you'll notice that all the studies we found have more than one observation. It's clear that the Walsh et al. Study is an outlier, but we'll later weight the observations accordingly so that no study has any undue influence. Next slide. We also identify the distribution of studies by water quality measure, but not all of them. There are 18 measures we summarized in the paper. By far, water clarity has the most observations, 260. It's a measure that homeowners might perceive compared to the amount of nitrogen or phosphorus in the water, which is why it makes it so popular in these types of studies. In addition to water clarity, we have fecal coliform as a measure of water contamination, chlorophyll A as an amount of algae or the trophic condition of the water body, measures of nitrogen and phosphorus, as well as pH. And these numbers on this slide include both waterfront and non-waterfront observations. Next slide. So the third step is to code the variables. I already mentioned formatting elasticity estimates as the summary measure of interest and the water quality measures, but we had roughly 100 variables coded from each study. We coded study details like the year of the transaction data, the type of publication, whether it was a peer-reviewed journal article, a working paper, or the thesis. We included a functional form estimated and other methodological choices. We included the region or population characteristics, We included the water body type as well as the baseline water quality that was included in each study. Next slide. Our next step is to calculate the summary measures for the mean elasticities. And these measures can provide unit values that we can then transfer to other policy locations if it's deemed appropriate. So as opposed to function transfers, which I'll show later, I mentioned having multiple observations from the same study, especially the same water body, and this can lead to mean elasticities that are misleading. We refer to this as clustered nature of data. You can imagine one study with many observations like that Walsh et al. That have the same underlying value may lead to higher or lower mean elasticities because of the number of observations. So we weight the estimates accordingly. We define a cluster as a unique study and housing market combination. No matter how many elasticity estimates are provided by one study for a given location, each cluster is given the same weight. We do this for both waterfront and non-waterfront homes, so we have separate elasticities for those categories. In addition, we weight more precise estimates. In our study, the weights are based on the random effect size, which takes into account the variance of the estimate. I won't go into detail, but we described this approach and why we chose it more in our paper. Next slide. So here's where we present the weighted mean elasticities. We find some unexpected results, but generally they would match our expectations. So let's look at how we interpret these numbers. For water clarity on the far left, we have both waterfront, which is in blue, and non-waterfront estimates in orange. A 1% increase in water clarity, which means clear water, leads to a 0.105% increase in home values. For non-waterfront homes, a 1% increase in water clarity leads to a 0.026% increase. Those three asterisks show that the elasticities are significant at the 0.01 level. Waterfront home values are affected more by water clarity than those homes out to 500 meters, and we would expect to see a stronger effect closer to the waterfront. So what we found is that the better the clarity, the higher the home price, an increase in price. But for fecal coliform, chlorophyll A, nitrogen, and phosphorus, which are all contaminants, they decrease the home price. Sorry about the siren here. Some unexpected results. We have a strong non-waterfront effect with fecal coliform compared to the waterfront. We have a positive non-waterfront effect with chlorophyll A. We also have an insignificant mean for non-waterfront homes and phosphorus. There's no asterisks. In any case, that's what the literature shows, and we can use these weighted means for the unit value transfers. Next slide. So step 5 is to run the meta-regression. And in the case of water clarity, we have enough meta-observations and studies to do a more complex function transfer, which is useful for benefit transfer. Again, we have the 260 observations for water clarity. Next slide. So for all the water clarity studies, we use the cluster means that we used in elasticity calculations so that no one study biases the summary statistics. Those variables with the subscript A represent dummy variables. That is, we coded them 0 or 1 depending on the study. For example, waterfront home estimates would be coded 1, while non-waterfront homes are coded 0. The summary statistics for waterfront is 0.5, which means we have about half waterfront observations and half non-waterfront estimates. Our mean clarity is about 2.2 meters. We have about half observations for estuary and half for lakes and reservoirs. Mean house prices are around $223,000. In the earlier map where our studies were located, we included the regions. These are coded as 0 and 1 as well. We have about 17% Midwest observations, 55% are from the South, and 2% are in the west. And this leaves about 26% in the northeast. And again, these are the cluster weighted, which would differ from the number of studies you saw in the previous map. We also have a variety of methodological variables, such as 9% of our observations were unpublished, 7% of the observations used assessed values from an assessor, as opposed to actual values from the market. 2004 was the mean year of the study, and on average, studies used about 11 years of sales data. We also included some functional form variables for the different statistical models, like linear, log linear, and double log model was being held out as the baseline. Next slide. So to estimate the regression using clarity data, we use the same cluster adjusted random effect size weights, but now we have one additional complication. That is, we may have unobserved effects within the same cluster. That is, from the same housing market, same water body, we may not capture all the important variables. And this would affect our error term when we estimate the model, or the error terms would be correlated for observations from the same cluster. We ran a variety of models, but chose one called the weighted least squares using the weights. Some literature suggests this is preferred because we include a measure of precision, in this case, the elasticity variance, as one of the methodological variables. For the model, we have our price elasticity for water clarity for both waterfront and non-waterfront homes as our dependent variable. Our independent variables include the waterfront and estuary dummy variables. And we also have a baseline water clarity variable. We also interact the estuary dummy and the baseline water clarity to see if estuary water clarity affects home prices differently than lakes. We have the median income from the housing market, which comes from the census, and we include the 3 regional dummies and a few of the methodological variables. We use 18 studies. Again, we had 260 observations, and there were 63 unique housing market combinations that we used as the cluster. Next slide. So here is our preferred model. The significance of the variables is shown with asterisks. 3 means it's significant at the 0.01 level, 2 significant at the 0.05 level, and 1 asterisk is significant at the 0.1 level. The variables are listed in the left column. We see that waterfront homes have significantly higher values with respect to water clarity by 0.047%. We see the higher the mean clarity, the higher the home values, but this is insignificant as our homes near estuaries and the interaction of mean clarity and estuaries. We see the regional dummies have a significant effect on elasticities related to water clarity, with Midwest, South, and West all having negative signs. This suggests that the elasticities with respect to water clarity in the Midwest, South, and West are all significantly less than the Northeast. We also see that unpublished studies have a significantly larger elasticity than those that are in the peer-reviewed literature by about 0.05%. Finally, our time trend variable has a significant positive sign, suggesting that elasticities have been increasing with the time of the study. I also have some additional methodological variables we included in some of our other models, but for the most part, they're insignificant and were not included in the model I'm showing now. Next slide. So to use these results in benefit transfer, we must consider the average elasticity observation, where we plug in the cluster weighted mean values for most of the independent variables, or 0 or 1 for the dummy variables, and use the estimated coefficient to estimate elasticity. If you look at column 2, those are just the results from the previous slide. Column 3 represents the values we would plug in for the average elasticity. So for example, suppose we want to know what the average elasticity of a waterfront home in the Northeast is. we would plug in a 1 for the waterfront dummy. We would plug in the averages for water clarity, estuaries, median income, and unpublished studies. And we would plug in zeros for the 3 regional dummies, so this model represents for the Northeast. For elasticity variance and assessed values, we plug in 0 to reflect best statistical practices. We set the time trend equal to 20, which corresponds to 2014, our most recent study year. We multiply these values by the coefficients and add them up. So in this case, a 1% change in water clarity for Northeast waterfront homes leads to a 0.37% change in home values. Next slide. As opposed to waterfront homes, let's take a look at the difference for non-waterfront homes. The only change in the values we plug in is turning the waterfront dummy variable to 0. So in this case, a 1% change in water clarity for Northeast non-waterfront homes leads to a 0.32% change in home values, which is slightly less than the previous slide, waterfront homes. Next slide. Finally, we can look at the average waterfront home in the Midwest. Turning the waterfront dummy back to 1 and changing the Midwest dummy to 1, we see that a 1% change in water clarity for Midwest waterfront homes leads to a 0.21% change in home values. All of these examples had significant elasticities using our Monte Carlo simulations. However, for average elasticities corresponding to waterfront and non-waterfront homes in the West, those were statistically insignificant. Next slide. So I just walked through our estimates of elasticities for different water quality measures, and based on our meta-regressions for water clarity, when feasible, it makes sense to use local data and local markets to look at the effects of water quality changes on home values. But for broader studies or where studies don't exist, the implications are pretty clear. When it comes to benefit transfer, the question becomes whether any particular water quality decision can be modeled for the water quality measures. That is, if we have a national policy that affects water clarity and we can measure those potential changes, we could use our function transfer and differentiate our elasticities by both waterfront and non-waterfront homes and the specific U.S. region. Now, because most agencies, state, federal, don't regulate clarity, this would require translating the change in water quality from the decision to clarity, an extra step. However, if the water quality decision affects other water quality measures and those changes can be predicted, the best we can do is the mean summary transfer, which would have the same elasticity across all regions. Next slide. So based on the literature search and our findings, most water quality parameters do not have sufficient observations to estimate the functions. The value transfers may only be viable, may be the only viable approach to examine these effects unless more studies are completed. We do find that water clarity is capitalized into property values, but when we tested our benefit transfer results, the errors from our meta-analysis are fairly large. Although I didn't present this, we did run tests to see how close our function transfers were after holding out observations from each of the 63 clusters one at a time. And when we compared that to the new predicted elasticities to the excluded cluster, the errors were on the high end, but similar to those found in economic meta-analyses literature. Next slide. So we now have a tool that can provide elasticities related to home values and water quality. One of the contributions is our metadata that we created with the Hedonic water quality studies. Combining our elasticity estimates with spatial data of water bodies, housing, and housing values, we could assess national decisions in an integrated assessment model. And that is one that includes both a water quality model and benefits assessment. Now, there's a paper by Corona and others that describes such an integrated assessment model being developed at EPA, and we're beginning to think how we could include our hedonic meta-analysis in that model. We also plan to make our meta-analysis and data set publicly available and to periodically update that data set. And after looking at what we learned from the literature search and the meta-analyses, with our remaining time, Mike's going to discuss some potential future research directions. Thanks. Next slide.
All right, thank you, Matt. So yeah, the question then becomes, so where to from here with our future research? And I think two of the biggest gaps or directions for research that can be seen actually from just looking at some basic summaries of the metadata that we collected. And the first is, I mean, just from the map of where studies have been completed, it's clear that there's significant portions of the country and different regions across the country and their water bodies that don't have any studies. And in this map right here, the dark blue indicates those are actual counties that have had a hedonic study completed. The light blue were hedonic studies that were completed in those states, but where we couldn't actually identify the particular county where that study was done. And so there's a lot of work to be done, and there's a lot of gaps across the country that can be filled. The second gap that I think that we found from just an overview of the literature is that most water quality parameters are not widely addressed, and we're really lacking evidence from multiple studies examining different water quality parameters. And as you can see from here, you know, most of the hedonic studies have been done on lakes and reservoirs. A large portion of them, as Matt said, have been done on water clarity or light attenuation or things that have to do or are similar to water clarity, but very few studies have been done on other water quality parameters looking at E. coli or total suspended solids, dissolved oxygen, etc. So I think there's some real big gaps there. And the third thing is that, you know, the studies that we examined were over kind of a wide period of time, and so the methodologies used in those different papers sort of evolved over time. And so that could be one reason why, you know, some of the results from the meta-analysis maybe weren't as robust as one would hope for. So where can we fill the spatial gaps? What water quality parameters are available that are suitable for hedonic analysis? And which water quality parameters are most likely to be affected by policy decisions? And related to the first point in terms of the spatial gaps, I mean, I think an important question to ask and address in future research is how, you know, might people's preferences and values for water quality improvements vary across the region? You know, is it homogeneous? Do people feel the same about water quality across the country, or is there some, you know, regional variation in that? And that's a question that I'd like to address in future research. Related to point two, optimally, we'd like to have water quality measures that show substantial variation across space and that are measured frequently so that they can be matched with the time frame of the property sales data. And so that's usually in conducting these hedonic analysis, one of the biggest challenges is finding water quality data that can be matched with the property sales data in an appropriate way. And that remains a challenge to this day. And then thirdly, you know, knowing which of the water quality parameters are likely to be affected by policy is not directly included in the hedonic analyses, but it's an important question to ask to inform the design of future hedonic studies. You know, we'd like to be able to evaluate the effect of policies and programs on changes in water quality and how those are translated then into economic benefits. And then we can use those estimates of economic benefits to then inform and adapt those policies and programs to lead to more efficient outcomes. So one of the ways that we're moving in order to meet those challenges is Zillow makes available to researchers, they make available their data, which is nationwide data. And the Zillow data is extensive, but it's not complete, and it doesn't include parcel boundaries, which is one of the limitations of the data. Now, those parcel boundaries are available in certain states and are publicly free, but in other states they're not free. But from what this, from this map, you can see, while not complete, the Zillow data does open the door to conduct hedonic analyses in a lot of those regions across the country that haven't been examined before, and to conduct regional studies to fill some of those spatial gaps. But as I mentioned, the sales data is just part of the challenge. Obtaining water quality data that's on the appropriate spatial and temporal scale is also a large challenge. And so we do currently have a data sharing agreement with Zillow, and our future research is planning on taking advantage of that or leveraging access to that data. So on the water, in terms of obtaining water quality data that can be matched with property sales data, one exciting avenue to pursue for the water quality data is leveraging remotely sensed data. Generally, these remote sensing data provide much more data points or measures across both space and time relative to in situ collections, but it's not always the case. But for example, now we're able to measure chlorophyll A, and there's some studies out there on water quality that can measure these things or obtain a metric of these things across a wide number of water bodies across the country, and are generally measured quite frequently, anywhere from every week, if there's, it depends on the cloud cover, to monthly, and it also depends on the sensor. But satellite data won't necessarily resolve all of our questions. The smaller lakes and rivers are much more difficult to measure with remote sensing data, and the types of water quality parameters that can be measured with remote sensing is fairly limited at this time. So this is from a study that was recently done, a literature review of water quality parameters that have been measured using remote census data. And these are the number of studies that looked at these different water quality parameters across different water body types. And what you can see, it tells a similar story to the hedonic studies that we found. Most of the studies that have used remote sensing data or are measuring those water quality parameters from space are examining chlorophyll A, suspended solids, and clarity. But there's a bunch of other water quality parameters where there's a smaller number of studies. And as remote sensing technology progresses and more and better sensors are developed that are intended to look at inland lake water quality, I think that in the future this will be a really nice avenue to pursue. So finally, some of the additional issues that we'd like to address in our research, and that I think we can start to address with access to property data across the country, and potentially leveraging some of these remote sensing data sets that are available across a large number of water bodies and at a high frequency. But this consistency in data sources and modern econometric methods, hopefully will lead to improvements in both the internal and the external validity of our benefits estimates. We were kind of getting a few mixed signals in the meta-analysis, and that's likely to do from the wide range of methods used in those studies, the different ways of including the water quality, etc. These high quality estimates can also be used in future regulatory analysis of regional and nationwide water quality criteria and regulations. To date, property value studies have not been incorporated into any of EPA's official cost benefit analyses. But I think as we move forward with this research, the hope is that, we can instead of sort of, acknowledging that those values exist, but not having a good robust measure for those benefits, we'll be able to include those in the future. And also being able to conduct new studies in different parts of the country using different water quality measures will also help support more local decision making in environmental and public policy. I mean, we'd like to be able to measure these economic benefits at a very broad scale, but the same studies, we'd also like to be able to provide those results to in the context of local decision making as well. And so with that, here are some of the references that were mentioned throughout the presentation. And again, we'd just like to acknowledge our colleagues at Appalachian State and Apt Associates.